And good morning, everybody. First of all, I would like to thank a workshop organizer for inviting me here to report our recent serious work on the topological bands. Here we have many students. For the first half part, I will introduce, give some introduction to the background for our work. Then in the second half, I would like to report our recent two experiments, for realizing and manipulating the exotic topological band and their unique topological properties. Okay, this is an outline. First, I would like to talk about our motivations. Actually, we start from a different route, normally from chain insulator, integer Hall, quantum Hall effect. We actually start from other system, like gapless, the helium 3A. So I will talk about, and I will give some introduction to the background for the what is topological classifications of the band and the connection to topological gapped system. In particular, I will talk about some symmetry protected Z2 topological metals. And I will also introduce our finding that there are also additional 4 new classes, the topological gapless band, so-called the PT symmetry and the CP, the charge conjugate and parity symmetry. I also report our collaborator work on some experimental realization and manipulation using the superconducting quantum circuit. If I have time, I will tell some conclusion our research on the topological metals with disorders. Okay, then there is a summary. Okay, and I think most of us have been quite familiar with so-called topological insulators, some gapped systems. The most representative is the integer quantum Hall effect. And there are also some the hard research on the topological insulator that is a symmetry time reversal symmetry protected gapped system. And also the particle Hall symmetry protected, sorry. Let's see. Wow. Okay. Protected superconductors. We know that they have some topological stabilities against the weak perturbations due to the non-trivial topological number defined for the bulk. Okay, there are some classification for the TRS and the TCSS. Then about I think 5 years ago, we started to think about the other some issues. How about the gapless system? For example, the fermionic metals, that consists of the Fermi surfaces, Are there 2 topological characters connected? One is a gapless, the other is a gapped. What are novel for this kind of topological metals? So for the past 5 years, we have made effort to answer these questions. Okay, let me give some background. We know that once we started solid-state physics, we know that for the fermionic system, we have the Fermi surfaces. Let us consider some the ground state, for example, at 0 temperature. Then there are some gapless points or the surfaces. For free fermion in the momentum space, d momentum space, so we have a d minus the surface. Then we have some our paradigm, non-Fermi liquid theorem. When there is an interacting fermions, the situation is quite complicated. There may exist a Fermi surface, there may not. If there are Fermi surfaces, they are sometimes stable, sometimes unstable. And also there is various configurations. The point, just a Dirac point or Y point, and 9, nodal 9, and also the surface or in the high dimension various shapes. For those kind of surfaces, it is noted that some are rather robust, some are not. So any topological origin Actually, there is a very beautiful answer for the one kind of class without any of the discrete symmetry. This in the Volovik's book, okay? Then the Horova proved using the topological, algebraic topological theory, K-theory, to prove that his classification or his understanding is mathematically sound, solid. Okay, then we start consider this as using some idea of the Volovic. We try to consider some symmetry protected. Most are anti-unitaries because these are robust against the many kinds of the weak perturbations. This anti-unitary, normally we are quite familiar with time reversal, particular particle Hall, and on. So actually then we try to consider this. We also use the K-theory. We found originally there's a Z-type. Z-type, that's any integer number, just like the integer quantum Hall and helium 3A. So then we find that with the restrictions, some of them are still Z, but some of them become to Z2. I will tell them in detail later on. Okay, then start from we do not start from the pattern, we just from the propagate or Green's functions. For example, we're choosing the EF equals 0 for simplicity. Okay, then what is the Fermi surface? Actually, the Fermi surface is at the 0 point of just the pool of this inverse of these Green's functions. So this inverse of this is invertible unless omega at 0 and k is in the surface. So there is the pool in this one. So for the Fermi surface, actually it's for any kind of topological bands. Here we talk about Fermi surface. It is noted that there is an important the quantity appeared here. It's called the codimension. We are quite familiar with it as a momentum. In the momentum, the dimension of the Fermi surface, we define it as the DFS. But codimension is different. It's the difference of your momentum dimension, momentum space dimension, and the DFS. For example, in 3 dimensions, if you have a point like a Fermi point, it's 3. If we have loop 9, then the codimension is 2, which plays a key importance. It's a relevant number for the topological properties of the Fermi surface. Okay, mathematically, it's actually is described by some a homotopy group. Okay, then it's described that has a Z type. Normally, is for the pi p equal to 0, 1, 2, 3, just like the integer quantum Hall effect. Okay, then how to calculate this homotopy number? It is just like the Gaussian theory. You construct some actually the transverse loop to include your singularity. Then you will find if it's 0, it's non-trivial. If it's non-integer number, this is a topological one. Okay, actually, as I mentioned, this is rigorously ensured by the algebraic topological theory. It's also called the K-theory. Okay, let me give you an example. For example, for the so-called A class, just like integer quantum Hall effect without any symmetry, or helium 3A, okay? Then you will find if the topological stable Fermi surface only exists in the other dimension, okay? Just like you can find the codimension. The codimension is odd. For example, the y Fermi point is in 3 dimensions, so you have a 0, so 3 minus 0 is 3. So this is topological stable. However, for example, in even dimension, you will find without any symmetry, then A class cannot be exist. This is a general mathematical principles, okay? So you can use this first criteria to judge whether there is a possibility to exist some topological A-class. But in addition to this one, there is the other kind is called A3. The A3 is it does not have the A-class property, but it has some so-called the chiral symmetry. That is, there is the operator anti-commute with the Hamiltonian. And for example, for some graphene-like system, this has a chiral symmetry. So for this one, there is also a kind of the topological stable. But please be attention, this is a symmetry protected. And also, there is an important result. There is a one dimension shift. For example, for A-class, in the codimension is odd, but for the A3, only even. Okay, this is a general one. Okay, here there are some already formula in Volovik's book. For example, A3 A phase, there are two Fermi points. Okay, then you can find it's topological stable. However, in experience, you can find some Fermi loop, okay, that kind. Then if you introduce some weak perturbation, then these Fermi loop are not stable. Okay. So then for the one dimension, you can find P equal 2. So therefore, they are not stable. Okay, initially once I deliver such kind of the talk about 3 or 5 years, I use the Y point. At that time, it has not been discovered in condensed matter as a periodical example. This is a wire formula. For example, you may have a positive harmonic or negative. Then it's easy to calculate the homotopy number. You find out +1 or -1. For the gapless system, and I think they borrow some terminology from the high energy physics. It's called the topological charge. Okay, while for the gap system, we call it a topological number. Okay, some also call this as a winding number, okay, conventionally. Okay, then let me make some comparisons between these two systems, because most of us are familiar with that for the change the gap system. For topological gap system, if we also use a homotopy language or homotopy class for the Green's functions, that means this is for the whole omega indicating whole space. Then once you calculate the chain number or topological number, you need to take the integration over all the field band. On the other hand, for the gapless system, here the key quantity is a P, okay? It's a D minus DFS. And also here we choose some any kind of the sphere with the P dimension to include this Fermi surface, or you call it some singularity around the transfer dimension. Then you are able to get the so-called topological charge. Of course, all of them do belong to the homotopy class. So essentially, they are the one thing for the two phases. Okay, actually, you can find from the algebraic topological theory, they are almost the same thing for some system. Okay, not for all of the system. For interacting for some other, they are not. I may give you some example. Okay, now let us consider some for the condensed matter system. Here I will focus on so-called the extended topological sense, the time reversal and the particle Hall. These are two representative anti-unitary. What is called anti-unitary? That means it's a product of the unitary operator times the basic anti-unitary. This is a complex conjugate. Although you can find the anti-unitary is operate times its conjugate, its hermitation equals to 1, but it's different that this is a nonlinear operator. Okay. So once we decouple this the small gamma, this is a mathematical one. We can actually it's the same as t squared can be equal to +1, -1, or trivial equal to 0. So normally for each of one there are 3. Okay, then particle Hall symmetry will also have a 3. So 3 times 3, we have 9 classes. This one. Then in addition to this, you can find that the conjoint, the C and the T, okay, will also give you the same some unitary, okay, because both are antineutrals, so C and T unitary. This is, or we already know the chiral symmetry. So for system, we can have a chiral symmetry, but does not have C and T. So totally, we have 10 classes. This is a famous Cartan classes for the Hamiltonian or for the homotopy Green's functions. Okay, I list this all of the 10. The 2 of them have already been studied, the A and S3 class. What we have done is about the remaining the 8 classes. Okay. Then here I can give you some what is the key point we considered. We consider actually both in the above the particle Hall and type reversal operations. The key, all of them, the K is the make the operation to minus K on the Fermi surface. Here I show this one. So then we have some restriction on the original one, for example, Z system. So therefore, actually, if we are using the K theory, then you will find that, therefore, we have a topological without any restriction or symmetry. Then this is we call the fundamental topological charge. Normally it's Z. Then it has the first descendant, okay, the sun and the ground sun, Z2. Then we find that both are Z2. Similarly, for the S3, they also have the other kind of the families. So totally, then we can produce some so-called periodical table for all Cartan classes, 10 classes. Here I just will show you one, the very famous one is A2. It's a topological insulator, okay? Then you can have 3-dimensional, the initial the Z, and it's the sun and the ground sun. Then it does not have the third generation. Why? Because Z2. Later you will see if the third generation, then it's end. So the periodical table is 8. So this border periodicity is 8. Once we produce this periodical table, it's surprising to us. It has some very good correspondence to the original find for the periodical table for the gapped system. Okay, that is listed in the right hand. This is for codimension. This is for real momentum dimension for topological gapped system. You can find for the topological, this is a class does not correspond. They have a one-to-one correspondence. Of course, physically, we can understand if you have a topological insulator or quantum Hall system, then you have the gapless system, the AG modes. Here, actually, we do not consider the same system. One is, for example, Hall world of the gapless. The other is Hall world for the gapped. For one system, you have such kind of one-to-one correspondence. For the different system, we can also prove this one using the rigorous mathematical theory. Okay, in addition to this, this is about the topological type. Then for the one system, then we know that for integer quantum system, you have a one-to-one correspondence. So then we prove for the other symmetry protected one. Yes, we also have the general index theorem. This is a topological charge, number of topological charge. This is our chain of topological number. Okay, you can find here the D is the space plus time using the high energy representation. So you only have, you can see, not only the topological class, you have a one-to-one correspondence, also the topological index. This is an index theorem. So you can see that topological protection, you can see the originated from the gapless edges, and you can also view it from the gap. So they are the same thing, okay? This is a quantitative description. Okay, in addition to this, we also find for the above 8, the Z2.
So how is that you derive this general index theorem? How is that?
Using the topological invariant, you can read our long paper. We spend a long time to, although we have understanding that physically we should have this one, but the mathematical proof is highly non-trivial. We use the topological invariant. We use the, for example, the Dirac, the algebra, Cliff algebra for 4 pi 4, construct all possible, then you can, one calculate the topological number, you can prove it. That's a tedious derivation or the proof. Yeah, ideas is applied to the integer quantum mechanics. Yeah, yes, we motivated by we use some of his theory. Yeah, it belongs to the topological, the algebraic topological theory, but not all of them. This the left-hand side is the.
The reference. What are the references for this derivation?
Oh, sorry. You can share. I also show the front page. Yeah, that's a mathematical in the a long paper about I forgot it's a long paper in the one of PRB. Usually we submit to PR. One says very good, the other say it's too mathematical, so you can put a long paper for the readers. With you can read it for all of this one. Of course, for the A and S3, it has already been proved. But for the other symmetry protected 8 class, we prove it. Also, we personally guess it, then we prove it. Okay, yeah, you can find it later on. I will talk to you. You can find my reference list in the front page. Then for the above 8 classes, the Z2 point, we also have some new findings. First, this is any high dimension, we consider any, you have for a parameter space, many high dimension. Any high dimension Z2 Fermi surface is topologically equivalent to a Fermi point. Okay, this is very good for theoreticians. So we proved this one, okay? For example, you have 40 dimension, okay, the parameter space. If you have some Z2 Fermi surface, then you just collapse them to the one point, treat them. This is one. The other, we prove some unconventional strong no-go theorem. As you have already known, for the y point or something, there is the no-go theorem. The total summation of topological charge is 0. But here for Z2, we prove that Z2, sorry, we should explain, it depends on the parity, even or odd. We use 2, 0 or 1. Then we find if you have a 1 Fermi point in this periodical, the above system is 1. All of them are 1. If you have 1, 0, all of them are trivial. So you need not, initially you reduce some the complexity to very simple case. Also, we prove this one. Besides, in order to collaborate with experimentalists, we list all possible, for example, using some simple one. For 3 can be represented by the polymetrics. The other 3 can be represented by the Dirac matrix. Or from previous table, you can find there are only 6 types of the Z2 Fermi surface may exist here. So we here give for the physical dimension d equal to 1, 2, 3. Then we give all the example. Some of them have already been realized with our experimental collaborators. Yeah, this is a formula. This is a Hamiltonian. But initially, it's some mathematical proof just using topological invariant.
So my question is, are these by trial and error, or is there any systematic way you go from H1 to H2, etc.?
Yeah, there's a different. If you have a different symmetry, that are different physical system. We start from the up. We consider general principle. Then we construct the Hamiltonian. Then compare with the real system. These are 3 Z2 topological methods. 3D, 1D. Okay, for this kind of the physical access system. Okay, this is not my main point. It's just our previous work. Okay, this is an example how to calculate the Z2. Use the extension the previous one. Okay, now let me introduce our recent finding. As I noticed that there are already mentioned that some PT symmetry. Actually, well, PT is a very important symmetry. P is the parity, or we call it inversion symmetry. The T is a time reversal. In some systems, if the system has both P and T, okay, the PT is. But we still have a system that has neither P nor T, okay, but have joint symmetry, PT. This is I think the more universal or general than the time reversal one. we noted that this is also anti-unitary the operations. But here we find that this is different from the previous. I talked about the Cartan classes is a new classes. So we're using some Cliff algebra. Of course, also use the algebraic topological theory, borrow the theorem. Then we find the key observation, both PT and CP are some local in the momentum space, unlike the previous K minus K. Then we give the mathematical classification, 4 new classifications. One is that the square equals to positive 1, the other minus 1. Okay. Then we construct all the relevant model using some simple for 2 by 2, or sometimes must have the 4 Hilbert space and Hilbert dimension construct all of them. This is our theoretical. Then I'm thinking about how to realize this one. Of course, we know that there may exist some system, but it may be some relatively easy to be simulated or realized in some other kind of system. Here I give you a simple example. For example, if we have the PT square equal positive 1, so that if first we start from both P and T, so you can find this Hamiltonian easy, okay, to satisfy the both P and T. But when we add these perturbations, you will find T or P are broken. So therefore, no T and P, but have joined the PD. This A, I use this as sigma 3 times anti-unit vectors. Then this is as I'm sorry. This is Z2. So how to verify Z2 lecture in experiments? So the simple one is you have a double version. Because Z2, unlike the Z, if you have the 1, then you have other one, they become Z equals to 2. But for Z2, if you have 1, you have another 1, then Z equals to 2 is trivial. So it's not topological protection. Also, you can find there is, if we're in the 4 dimension here, I show you, you have this kind of, this is commutated with the original diagonal Hamiltonian. But so the symmetry is proved, but then you will find the gap can be opened. This is also the Z2 lecture. You cannot have the 2 of this system. Okay, then lattice version. This is a continuum version. Okay. We think about it. The lattice version is very simple. So once I saw this lattice version, because I have also doing some work before on the quantum computing, so I considered some system for using the qubit. Here I give you some the ancient Chinese the cartoon for the PT symmetry. Black and white is a time reversal, the day and night. Okay, the position is like this one. So if you make the inversion or you make the time reversal, the system is changed. The symmetry is broken. But if you have the joint one, okay, you find that this is still just like the time sign, this one. If you reverse this one. So this is a beautiful cartoon to show the joint PT, the symmetry. Okay, then here I'm not the experimentalist. I just know how to. In the superconducting right now with the advancement technology, they have the very good cavity. Here I just using even the one single qubit. I can manipulate the 2-dimensional all of the. Here I wish to mention all the omega I, they're controlled by the Rabi, also some lasers can be precisely controlled. Continuous or you let them periodical or whatever. Here I just write the 3 sigma, then sigma 0 can also be added. Later on I will use it. Okay, so then refer to previous simple. This is the simplest Hamiltonian without interaction. I can construct even without interaction, but we start from some simple system and see whether we can realize this one. Okay, so then they control this one with some CAD. Then here I show you some experimental results. Here is measured for the parameter for the first principle. We use the cubic system. So you can clearly see this is the, you can call this is not the Dirac, actually it's Z2 is not Dirac point. You can call this actually this point, just like the Dirac cone, okay? This is a gapless. Okay, this is a measured energy spectrum. Here I wish to mention, using this system, not only we can measure the energy spectrum, we can also measure the phase, but it's quite time consuming, but we cannot give the whole the spectrum. But if we want to look into the one of them, so I ask here I draw one cycle, then you can find you can get some integer, okay? Just like a berry phase. Here I show you, I add some perturbations, but does not break the PT symmetry within the range. Okay, let me show you. Very simple. Sorry, here, okay, I can change the lambda or change some other things. Then the shape can be significantly changed. The point can be changed, okay, but the gap cannot be opened. Okay, this is protected by PT symmetry. This is one example. Then once I add the other term, for example, sigma 1 term, you have both, then you will find the PT symmetry is broken, so the gap is opened. Here I wish to mention that this gap is a trivial gap, it's not topological gap. Okay, normally, to my understanding, I noticed that for the 7th dimension, if you have this topological gapless point, then if you open the gap, normally it's not cannot correspond to symmetry protected topological gap. One point I also wish to mention, you may mention, there are many studies about the gapless system. There are also some study about the PT gapless system, but it is not protected, okay? But for gapless, it's topological protected. Then you may ask, if I using this, you can read our paper. We use this as a boundary. Once we constructed the gap Bork system, that Bork has another kind of symmetry. For example, the inversion symmetry or something. So they have two different symmetries, not with the same symmetry. So that is a difference for the PT one from the previous one. For Cartan classification, the Bork and the boundary have the same symmetry protected origin. But here, there are differences. If you have interest, you may read our papers. This is an experiment. Then we choose how to verify Z2 nature. It's nature. Well, I just like the environment. I let these two Z2 points, when I let them get merged, then the symmetry is still there, but you will find that the topological charge is 0. So the gap can be opened. Yeah, you can see from this one. We move, actually you can move in and move out, move them to the boundary, then you can find that the gap is opened, okay, using this experiment. How much time do I have?
About 9 more minutes.
Okay, that's good. Okay, this is about the PT. Then I would like to report the other one. And some people may not notice it, but I think some high energy physicists may know this one. Okay, using the above there, as I mentioned, I can control precisely or vary with high resolution of the sigma 0, sigma 1, sigma 3, sigma 1. So I can construct this so-called highly tunable for in cubic system, the Y metals. All of them can be highly tuned. Okay, in addition here, the chemical potential can also be tuned. For example, I can become from the, initially I have the 8Y position, I can let it become the more, by add some cosine term here, and also let them emerging without it become the 4 Dirac cones. Here I wish to mention the other very unique topological the property of this tunable the wire metal. That is called the chiromagnetic effect. As I know, it is noted by some high energy physics, but it has not been observed or detected experimentally. only find some evidence from some indication from some numerical calculation from some high energy model. But here we can using the field theory and get a very clean result, theoretical result. Anyway, first I show this translation. You can find in addition to the conventional, so-called the current introduced by Maxwell, okay, or the gauge field, there is additional so-called topological current. It's purely from the boundary, okay, or that's why it's a topological term, okay, regardless of the details. So you can find it has some universal constant as a coefficient. Here, what is a B naught? B naught actually is the difference of the, if I have 2, here I have the 8 y point plus minus the difference between these two. There, if I using the k, okay, as a momentum space, kx, ky, kz, and k0. K0 is the chemical potential difference. So here, not zero k is a b, b0, b1, b2, b3. This just like some gauge field. But here I wish to mention, many people confuse the Einstein. This is not the electromagnetic that one. That is A0, A1, A2, A3. Here I'm talking about B, a response to this kind of the gauge field. So that one, for the normal electromagnetic response, is called a chiral anomaly. Okay, this is a chiral magnetic effect. It's different, but many of them, although you can, here, what is the new here? If you apply for example, the whatever fictitious or the constant magnetic field, then you will find there is a current, or even you without introduce any electrical potential difference, there is a current exactly along its direction, whatever this magnetic field be along. This is a new one, even modifies, I think, the Ampere's law. Okay, this is purely due to the topology. This is, once you have the experiment, you should detect the other current, just to keep this term. Okay, here, of course, is the derivation is not to kind just some the field theory derivation, but the results are very simple. Of course, you should also be careful how to get this experimental, because here, as I mentioned, you have the at most I have at least I have the 8 y point, 4 positive, 4 negative. So you should be careful. Sometimes if you do not carefully design your experiment setup, they will be cancel each other. It's 0, okay? But here I can say maybe 2 or 4, depends on how do I control the chemical potential. Okay, these are some results. Here also the amazing, this is because it's a universal. If you divide it by these two terms, you will find this is exactly a universal constant. So this must be some topological origin, irrelevant to some local properties. Here we use some different methods. For example, I can change the shape, okay, the sign or some the sawtooth, okay, whatever, as far as they are theoretical one. This is can be done in experiment with the superconducting solid. I'm not sure how to do it with a real solid. Okay, here there are two. One is I change the shape, sorry. The other is I change the distance of the y point. Then you will get the different, all of them are different. Then you will find all of them collapse to the the curve. Okay, then here there is also advantage for this experimental setup. Here I do not have the real magnetic field. What we introduce just some fictitious magnetic field is a vector potential. Okay, you can introduce it into the experiment. We first characterize this vector potential. You get the linear one. This is the shift of the energy spatial due to this one, due to this introduction of the vector potential. Of course, in some other systems, this vector potential can also be introduced. Okay, finally, I just conclude some here I wish to mention one point. we set the topological protection for the y point. That is a protection for these two multiple. Once you need to verify the protection for the Fermi arc or its conductivity, you should prove that the transverse conductivity is protected by some topological term, for example, WZW term from field theory language. Initially, once you add the disorder to this system, it's a passing, because it's in the mean field theory, you have a positive and minus. So you will find the two terms. Initially, you will find these are cancelled to each other. So the topological may be destroyed. So what is the protection? Actually, is due to the surface or infinite. Okay, that there is a so-called the WZW term. Okay, that is a real topological term. So we derive this one. We call this as the anisotropic theta term. This is a topological protection one. And use this, you can find, normally this is the other so-called electromagnetic Chen-Sam term. This is the other term in the Y metal. This is so-called, we call it the gauge field. Okay, you can view this as a gauge field. We find that it's indeed protect, okay, this transverse conductivity. So actually, for the weak perturbation disorder, we prove it rigorously. Not just initially, physically, it's very clear. They argue that for each plane, you have the chain insulate. So then it has a topological protection. But it's not in theoretical point of view, it's not rigorous proof. So we made this question, and finally we find, initially we have some concern about the cancellation. Then we find a WZ term in the surface or the infinite away due to the current conservation. It must exist this topological term that protects your quantized transverse conductivity. Okay, so you have a very nice. Here I show the Cartan. In the momentum space, you can see the so-called this is the Fermi arc. Okay, for in the real space, and you can see the persistent this kind of current. Okay, then that's my short summary. Thank you very much for your attention.
Right, are there any questions? Yes, there are.
So there is a point I miss. I mean, when you started deriving this index theorem, that basically is connecting the bulk essentially and the boundary.
This is for same system, yeah.
Yeah, so, and then you went and extended, you made this Clifford extension for these new classes. So I missed the point. I mean, do you still have an index theorem in those classes or not?
Yeah, for you mean for the PT symmetry, right?
Yes.
Yeah, we do not have the.
So
but
you do
should
not have.
Yeah, for the same symmetry classes, we do not. But you have the index theorem for example, when this is the PT symmetry, for the bulk is some joint other kind of the discretized symmetry. That's different. The bulk and the boundary have the different symmetry. Because you know that at the bulk and the boundary, because the inversion is in the bulk, you may lose the inversion symmetry. That is due to the special feature of the inversion symmetry. But of course, it has also some other kind. We can use this as a boundary to have construct some bulk symmetry protector. But this is not the same symmetry with slight difference. Yeah, our paper we have discussed this very clearly. Even I wish to mention you mentioned the Z2, I mentioned the PT, that kind of it's a topology gapless system. It also has the edge state, but it's not universal. Depends on the direction of this one. If your line cut from the even Z2, then this is a trivial surface. If you along some other Z2 point, then you will find surface state is a non-trivial. So it's very interesting, but it's very challenging. We just give the general discussion. Yeah, but it's from pure theoretical point of view. Unlike that, so always that bulk, then you have a universal edge state. For Z to PT, it is not. It's a very special kind. But gapless is still topologically protected.
Okay.
It has not been noted before, yeah.
Okay, thanks.
Right, any other questions? I seem to miss the point because at some stage,
Which?
you mentioned about 6 classes rather than 10, because involved.
Oh, yeah, I mean that there are only 6 that is non-trivial. Let me show that. That's either Z or, yeah, here you can see this diagram. In the physical accesses, 1, 2, 3, these are physical accesses. In our real space, there are only 6 Z2. I just this diagonal, these 2 diagonal. Actually, 10 classes is along this one, A1 there, this one, yeah. That this is, I can call it 6 types, okay, Z2. But Z, I think most of us are quite familiar. Z is normally just an integer quantum factor, or Helium 3A. I think it has been studied in depth for many years, okay? But the Z2, it has some novel property. It has not been noted before. Actually, we actually just borrowed the key idea from Volovic. He used some physical insight, and the Holloway used and K-theory discuss the Z class without any symmetry. Then we applied the K-theory to discuss those with the symmetry protected. Particularly, we consider anti-unitary because we believe these are can call the topological protected in some sense. If you protect it by some lattice, if you have any symmetry, you correspond in some invariant. But this is hardly to say topological protected. I met some mathematicians, they only recognize our integer quantum Hall effect and the helium-3 like this one. These are why point that real topological one. It depends only on the dimension, okay, regardless of other things. For example, I mentioned this one. Of course, physics is different from mathematics, so we have so-called the symmetry protected. Anyway, any other? Yeah.
There are many types of characterization. There are some that are non-local, that they are not just simply from
Yeah. Yeah. Good. Yeah.
I agree.
Yeah, particularly some non-local one. Yeah. But the local and non-local it depends on the which the representation you look. In this one, you can call the local. The other one is a non-local. Okay. So actually, I think the mathematical one is the original operate, okay, in the without the representation. Then you can discuss its some properties. Okay, just like whether it has some homotopy group number or whatever. Okay, that is a mathematical point of view. Of course, physicists we will have the understanding of physical system first. Then we can dig out what is the mathematical origin. Yeah.
Also in the one of the experimental curve, your B field is applied along the x-axis.
Yeah, that's we can choose any one, but for simplicity, we choose along the axis because it's save a lot of time. Because we did the k along this one, so we shifted a little bit the kz. That is just a fictitious magnetic field. We know that just like the gauge field. That's a trick of experiment. In real material, you can apply the real magnetic field. Okay, in cold atom, you can also apply the gauge field. Or in some other photonic crystal or the sonic, the sound crystal, okay, they can do the same things. Okay.
Any other questions that?
Particularly from students?
Yes, particularly from students. Yes, please. Yeah, go on. Project your voice.
Hi. I want to ask because there's one slide when you show there's a fictitious gauge field where you just say it's different than the Cairo anomaly.
Good question. Okay. Here. Yeah, the Cairo anomaly, if we from is electromagnetic response is just like a transmitter. That's a response. We have the F mu, and etc. Then there with the key point is a vector potential A0 just for the electrostatic potential A1, A2, A3. Then this is the Carroll anomaly is a response. Then you can calculate the E dot B term. Okay. Here, what am I talking about? Once I have a magnetic, only a magnetic with aqua, then we have the other gauge field. If you find this here, I do not show it. The B0, B1, B2. B is what? B is the difference between the two wire points. Okay, that's different from real electron. This is the gauge field, the other kind of gauge. These are two kinds of gauge field. What I calculate this topological current is due to this difference of the B. B0 is the energy difference, the chemical potential difference of the wire point. B1, B2, B3 is a vector, just the two vector difference. So this is response to that. Then one component we find that is the universal topological one. That we call. Then after we find this one, I told myself that we should check the Google Scholar. There must be some paper discuss this one. Then we find two or three, some one published, the other some preprint to discuss so-called this. I borrowed the name from Carroll magnetic effect. It's called Carroll. It's different from Carroll anomaly. Okay, you have only the magnetic field, then you will find this current. This is different from Ampere's law. If you have current, you have the vertical the current. So, but this is purely topology. If you have a theoretical system, you do not have boundary vanishes. So this is a purely topological one. But of course, we need other one, the difference of the chemical potential for this one.
Oh, thank you. I want to maybe ask more later.
Yeah, maybe one last question in the back.
Thank you for your great lecture. I have a question, very naive. I saw there are two tables to classify a system. One is for CPT symmetry, and one includes the PT symmetry. Mm-hmm. And it is possible that for a system, for a same system, it is they have different. Has different classification for these two different tables.
No, yeah, just like you have the plane. Then if you have both one, then they coincide with 1 point. For example, for PT classification. Okay, if you have both P and T, then it will returns to the T, because P is a unitary one. So it come to the time reversal. They are the same. Of course, once you have a mathematical theory, you should, yeah, you are correct. They cannot be, you cannot either this one or this one. They should be the same thing. Just like you have a plane, then the P, both P and T is 1 point, but I have neither P. The PT is a plane. Okay.
I mean, sometimes the system can have PT symmetry while do not have P symmetry or T symmetry.
Yeah, that's what I'm talking about. Yeah, this is a plane. But if you have both P and T, this is 1 point. That is belongs also to the T symmetry. So T symmetry can also be classified. They should be the same. Initially, previously, there are somebody discussed they have both P and T. Then they use the theory of for the time reversal B, because P is a unitary. If it's a unitary, it's equivalent according to physics. Okay, but here I'm talking about no P, no T, but PT. Okay, that's what I mean. This is
so. This can be called something non-trivial, other than the tenfold way classification, right?
Yeah, this is a four new classification. Yeah.
Okay.
The theory is also different. The other is we use the K0. Okay, it's if you're using the algebra topological theory, it's a slightly different. But of course, principle is the same. But they have a different. If this one is point to point one, the Clifford algebra seems the same, but they have some different. So you will find the difference. For this one, you can find we do not have the bulk gapped system for PT. But for the other, for the T, you have. If you have both T and P. So this is a beauty of the mathematics, okay? You can find it.
Okay,
all
thank you
of
very
them
much.
can be understood, yeah.